Welcome! In this video, I'll show you how to solve problem 8.10 as it appears in the third edition of Griffiths Introduction to Quantum Mechanics. Now, this problem asks us to do the following. It says, use appropriate connection formulae to analyze the problem of scattering from a barrier with sloping walls, which is the figure that we have right here, right? So we have a potential that is increasing, and then it is less than the energy up to a point x1, then it is greater than the energy, and then it begins to decrease, even though it doesn't really matter what happens here as long as the potential is actually greater than the energy. And then after some point x2, the potential will be smaller than the energy once again. So this is basically a barrier, but this time, unlike what we have seen before, the barriers are both sloping down. We don't have those just perfect infinite walls as we saw a few videos ago. Then they say, begin by writing the WKB wave function in this form. And well, we shouldn't assume that C is equal to 0. And we want to calculate the tunneling probability, right? So a few videos ago, again, going back to the case where we had just this regular square barrier, we found that the tunneling probability was approximately, of course, e to the minus 2 gamma, right? Because T is given by f squared divided by a squared. And what we had here is that this thing, basically f over a, this was simply e to the minus gamma, right? Where gamma is the integral. In the previous case, it was 0 to a of our momentum. But of course, what this represented was simply 0 was where our barrier began, a was where our barrier ended. So in this case, our barrier basically begins at x1 and it ends at x2, even though of course the walls are sloping, right? So it isn't quite the same as before, but it is just so that we can at least make a connection to what we saw before. Okay, and finally, we want to show that our result reduces to the equation that we found for this case, right, to our result here, in the case of a broad high barrier. Okay, so that's what we want to do. So what is the procedure? Let's go take a look at what we have to do. Let me get rid of these two circles. So what we want to do is exactly the same that we did in previous videos. So I've already discussed what happens in an upward sloping, basically how to find the connection formulas when we have an upward sloping situation and also when we have a downward sloping situation. I do recommend that you watch both of those videos because the procedure will be basically the same, except that this time it will be a little bit harder. So if you haven't done the easy case, doing this will be much more difficult. Of course, you should still be able to understand it in principle, but it will make things a bit more difficult. Okay, so what we want to do is we want to take both of these regions, right? Go to the intermediate regions because we don't have any problem with the region where the energy is greater or smaller. We have already seen that before. The areas that are troubling are when the energy is the same as the potential. So we go zooming in here and we solve the Schrödinger equation. We already did that. We know that the result are the Airy functions. And as we move away in either direction, we want our Airy functions that we call the wave function with the Airy functions, right? So we call it the patching wave function, which was a linear combination of our Airy functions and bi. So as we go to smaller and smaller x, we want our patching wave function to basically turn into approximately turn into our WKB. That's not very okay. WKB, and as we go to the other direction, we want the same thing. But of course, this is the wave function in this region. So I don't know. Let's call this region 1, for example. This is patching region maybe 1, and we can call this here patching region 2. And as we go into region 2, we also want the patching wave function to turn into the wave function for WKB in this region, which is 2, I guess. And we do the exact same thing then for the other point of interest. So we want the patching wave function here. Now the difference is that the slope is going downwards here, right? And thus there will be some minor differences, but still very important differences in the procedure. Okay, the general idea will be very similar, but there will be some small but important details. So as we go to the right here, to greater and greater x, what we want is that the patching wave function should turn into the WKB wave function in region, let's call it 4. And the same thing here, I don't know, let's just psi p has to turn into psi WKB in region 3. Okay, so this is a bit messy, but this is the general idea. That is the procedure. That's what we will do. And whenever we do that, we will get conditions, right? We will get a condition that link our constant a and b with our constants from the wave function. Now notice, when we do this, right, just looking ahead, we will get a condition between the first wave function and a and b. So we will link big A, big B with small a, small b, and also with c and d, right? This corresponding to this part. And then later we will be able to relate c and d with with small a and small. Oh, I just noticed I circled the wrong b here. I meant this one, of course. And then finally we will link f with these same quantities. Okay, so that's what we will be doing, just so that you can have an idea of where this is going. Now let's recall that when we were solving the Schrödinger equation for the linearization of the potential, what we encountered was the Airy equation, and we had to solve that, right? And that gave us the patching wave function. And the patching wave function, we found, or what we know, is that it is going to be a linear combination, as we just discussed, right, of some constant times ai of z plus some other constant b times bi of z. And ai and bi, we will use the asymptotic forms instead of the more complicated regular forms because it's much simpler and it is good enough for our case. Now, when z is much greater than 0, it has this form, and when it is much smaller than 0, we have this other form, which we'll use in a moment when we want to compare the patching wave function to the WKB functions that we get. Now notice that z is alpha x in the case for an upward sloping potential and minus alpha x for the downward sloping potential. And also in the case for alpha here, right, alpha is 2m over h bar squared times the derivative of the potential evaluated at 0 to the 1/3 power. And in the case for the downward sloping potential, so what I just said was for the upward sloping potential, for the downward sloping potential, it is the same thing, but the potential here, the derivative of the potential is in absolute value. Okay, so that is something we have to consider. And now we can move on and actually begin with the problem. Let's go for it. You can start wherever you want. I'm going to start with region x1. So let's take a look at this wave function. So in region x1, we're going to be dealing with these two functions, okay? Not with the other one. So what we can do is we can shift the axis, right? We always have the freedom to shift the axis of this integral because anything that we end up changing will be absorbed into the constant of integration. So for that reason, we can shift the axis and we can label it as follows. So let me maybe select this here so that I can copy it easier. So we'll just go off to the side here for a little bit and I will rewrite our equations. So now our psi of x, this is WKB, of course, WKB, and let me just write it explicitly. So at x equals 1 and renaming the variable basically, right? You can see it as moving the axis or renaming the variable, however you want to interpret it. And let's write it. So we go for this term, 1 over the square root of the momentum, and then we have a e to the I over h bar, integral from x to 0, right? So this is to the left, and then we have px prime dx prime plus b, and the same thing with a minus. So minus I over h bar, integral from x to 0 of p x prime dx prime. And I just noticed that I didn't put enough space for the other one, so let's fix that. So that is, this is valid for region when x is smaller, so x smaller than 0. And all that I'm doing here is simply rewriting x1 to 0, basically. Then we have 1 over the absolute value of the momentum, and then c e to the, now here it is no longer I over h bar, it is simply 1 over h bar. And we integrate from 0 to x, momentum, in the absolute value, of course, dx prime plus d e to the minus 1 over h bar, integral from 0 to x, and absolute value of the momentum. And this is valid for x greater than 0. Okay, of course, we are far away from x2 for now, so we don't have to worry about it, right? So this is, of course, still smaller than, in principle, if you want to be really rigorous, you say this is between x and x2. But of course, we're not really going to go anywhere near x2, which is why we simply say, all right, this is greater than x, and that's good enough. Okay. Now, of course, we need to find the momentum and the integral of the momentum. Okay, so the momentum, this is the square root of 2m, and now we get e minus v, as we have seen many times before. Now, what is the potential? Well, we are in the patching wave function, in the patching region, and as we have discussed when we first introduced this, what we do is that we approximate the potential to be linear. We say, all right, the potential is going to be some amount e, right? Because when you look at, I mean, we have talked about this in detail in another video, but when you go here, you are at a height e, and then you only have, this slope. So we approximate this as a straight line, which we can always do if we are close enough to the point. So e minus v prime 0. Well, this depends. It is plus in this case because it is upward sloping. In the case of a downward sloping curve, it is going to be minus. So e plus v prime of 0 and times x. So this is how we will approximate this. So when we plug it in here, we get square root of 2m e minus v prime 0 x. If any of this looks strange to you, I do recommend that you go back and either watch or rewatch the videos where we explain all of this, because it is not all that simple, and you have to understand it properly. This will give us square root of 2m, and then we have, well, e minus e, which cancel out, and we have minus v prime of 0 times x. Okay, and now what's going on here, you might say, because we have a negative sign inside of the square root. Well, don't worry, because we are in the region where x is also negative, so no need to worry about it. And now we'll do the same trick as we did in the other video. So we multiply and divide by h bar squared, because then we get the following. So if we multiply and divide by it, we get, well, an h bar, which we can take out of the square root, and inside we get 2m v prime of 0 divided by h bar squared, and this multiplies minus x. And why is this relevant? Because we can now go back to this little thing here. 2m over h bar squared v prime 0, this is alpha cubed. So what we have in the parentheses here is alpha cubed. It isn't really necessary that you do this, but it does simplify notation, and there's going to be a lot of algebra. So simplifying notation is something that you will really, really appreciate. So this is alpha to the 3/2, and then we multiply by minus x to the 1/2. Okay, so there we go. That is the momentum itself. Now, we can integrate this. So we integrate the momentum dx. And what are our limits of integration? We are in this region where x is smaller than 0, of course. So we integrate from x to 0. So we integrate from x to 0. And when we do this, let's see, so this is integral from x to 0 of, we have h bar, we have alpha to the 3/2, these are constants of course, so they don't do anything, and minus x to the 1/2 dx. I guess we should rename this and say prime so that there is no confusion. Okay, now let's take the constants outside, and we only have to integrate minus x prime to the 1/2. So this 1/2, right, when we integrate it increases, so it becomes 3/2. So we have to multiply by 2/3 to make up for it, and we get minus x to the 3/2. But because of the chain rule, right, we get a minus sign. And you can of course now make sure that this is correct, because if we take the derivative, we get a 3/2 that cancels out with this, and we get a minus that cancels out with that, and we get what we had before. So everything is fine, but we still have to evaluate this between x and 0. Now at 0, this is of course 0, so we are left with 0 minus this thing. So we get another minus here, so plus h bar alpha to the 3/2, 2/3, and also minus x to the 3/2. Now we have actually done this calculation before, but I'm just doing it in case you haven't watched the previous videos. Now we want to do the same thing, but for the absolute value of the momentum instead of the momentum itself. So the absolute value of the momentum, well, this is the momentum. What is its absolute value? Well, you can look at it as, let's just rewrite it. So absolute value of h bar alpha to the 3/2. And now let's write minus x to the 1/2 as the square root of minus x, which is the square root of minus 1 times x, which is I times the square root of x. And the absolute value of this is simply h bar alpha to the 3/2 and x to the 1/2. Okay, so now integrating this between 0 and x, right, h bar alpha to the 3/2 x, well, prime, of course, 1/2 dx prime. Integrating this, our constants do not change. And now what we have this x prime, it's going to be the same thing, right? So 2/3 and x to the 3/2 evaluated between 0 and x. At 0, it is 0, so we get the same thing, right? There we go. So now we have all the results that we need in order to rewrite this expression. So allow me to just zoom out, and I will begin copying this. So our WKB wave function, WKB, for this first case, so all of this is for x1. We will have to do this again, not exactly the same, but it will be the same idea, but for the other region. So side WKB, this is 1 over the square root of the momentum. The momentum is this. So the square root of that is 1 over square root of h bar alpha, right? So what I'm doing is I'm writing alpha to the 3/2 as that is alpha. So we have the square root of this. So square root of alpha to the 3/2 is alpha to the 3/4, which is alpha to the 1/4 times alpha to the 1/2. Right? I do this because just as we did in the previous case, in the previous problems, we will come up to a point where we can simplify alpha to the 1/4, which is why we do this. If you don't really understand, you can leave it the other way around. I'm just doing this because we have seen this in previous videos and it makes it a bit easier. And then we have alpha x to the 1/4, with a minus sign, of course, right? Yes, okay. And now we begin copying the rest. So we get a e to the I over h bar times this thing right here. But the h bars cancel out, so we don't worry about it. So we get I 2/3 and then minus alpha x. They have the same exponent, so we can put them together, to the 3/2. And then plus b e to the minus I, the h bar cancels out again, 2/3 minus alpha x to the 3/2. Okay, okay, my handwriting became a lot bigger by the end, but it's fine. Now let's extend this and we write the second part. So this is of course valid for x smaller than 0. So all these minus, this ends up being something positive. This is something positive, so don't worry. And then we have 1, so dividing by the absolute value of the momentum, which is this thing right here, we get the same thing but without the minus sign. So 1 over the square root of h bar alpha times alpha x to the 1/4. And then we multiply all of this, so multiplying times c e to the 1 over h bar, but h bar will cancel out, so we get 2/3 alpha x to the 3/2 plus d, and e to the minus the same thing, so d 2/3 alpha x 3/2. And this is valid for x greater than 0. Okay, so this is the hard part. We just did the hard part. And as you can see, just going back just a moment, what did we do? All we did was, okay, what is the relevant wave function here? And we used the one that was given. Otherwise, we would have had to come up with it ourselves, as we did in previous problems. And we just plugged everything in, right? We calculated the momentum, we calculated the absolute value of the momentum, we integrated it, and we also, well, of course, we shifted the axis to make everything be simpler. Otherwise, you are going to be carrying that x1 around, which doesn't really make any sense, right? There's no point to it. Now that we actually found the WKB function, what we need to do is find the appropriate or corresponding patching wave function for each region and then set them equal to each other. So we already know what the patching wave function looked like, but let's actually write it down. So there are, of course, 2 different versions for each region. So one for each region. And let's begin with the region where z is much greater than 0. So in that case, we have small a divided by, or times this. So we have to divide by 2 square root of pi z to the 1/4. And again, z in this case, since we are upward sloping, it is alpha times x. And then we multiply by e to the minus 2/3 z to the 3/2. Then we do plus constant b divided by the square root of pi z to the 1/4 e to the 2/3 z to the 3/2. Okay, let's separate these two. And then in the case where z is much smaller than 0, so very large negative numbers, what we have is some constant small a times this thing right there, so divided by square root of pi minus z to the 1/4 times the sine of 2/3 minus z to the 3/2 plus pi over 4. And then we get plus b and this other part, so divided by the square root of pi minus z to the 1/4, and then we get the cosine, so times the cosine of 2/3 minus z to the 3/2 plus pi over 4. Okay, so we wish to compare these 2 expressions. So what I have underlined here in green with, so that is smaller than 0, so we have to compare that with this one, and we have to compare this one there when x is greater than 0 with this one, right? Because when z is very negative, that means that x is very negative, because we are in the upward sloping case where z is alpha times x. So if z is positive, so is x, and if z is negative, so is x. So let's compare them directly. Let's begin with the one that looks the easiest. So in the case where x is smaller than 0, here we have the complex exponentials, but in the case of the patching wave functions, we have sines and cosines. Now we can, and we will end up going from sines to complex exponentials to compare them, but it is a little bit more work. So let's begin with the easiest one, even though it doesn't really matter which one we choose. So if we begin with the easy one, that means that we start with this. So let's just copy this expression so I don't have to rewrite it. And there we go. So I'm going to copy it and just move somewhere down here. And there we go. Just put it somewhere over there. Okay, so now let's compare these 2 expressions. So these 2. Now, comparing everything that goes along with the negative exponent, so basically comparing this term with this term, and of course considering the factors outside, we get that d has to be, let's see, d divided by h bar alpha inside of a square root times alpha x to the 1/4. This has to be equal to a divided by 2 square root of pi times z to the 1/4. Now, of course, keep in mind that z is equal to alpha x, which is why, of course, the exponents are the same, which is why this and this cancel out. So what we get here is that now you can see, you can choose whatever here it is that you want to solve for. Maybe we don't have quite the clear picture yet of what it is that we need to solve. The best thing to solve for is small a, because that is something that is part of the patching wave function. We don't really want that in our end result. So we solve for small a, which will also appear in the, when we go for x2, right? When we go for the other half of the problem. But if you are not quite clear yet, don't worry, just leave it like that, and eventually you will know what you need. So either way, let's go. So small a, this is 2 times d times the square root of pi divided by h bar alpha. Okay, just double checking. Okay, and now we do the same thing, but for the positive exponent. So in the case of the positive exponent, we have to compare now c with, of course, all of those constants and this term right there. So we get that b divided by the square root of pi times z, which of course is alpha times x. So we get alpha x to the 1/4. Here also you can see why I chose to group alpha and x before. But again, it doesn't matter. Here you would have just had to see that you can do that. And this has to be the same as c divided by h bar alpha times alpha x to the 1/4, and this is inside of a square root. So from here we get that b is c, this cancels out, times square root of pi divided by h bar alpha. So here we go, we found our first two conditions. Now we need to do the exact same thing, but for the other region. So I'm going to get rid of some of these things because I don't want to have so much chaos going around. So I'll just get rid of some of these lines, maybe get rid of this. And that way it will be a little bit less chaotic. Okay, so now what we want to do, and actually maybe I can even move this and reuse the same space for the other case. So I'm just gonna put this somewhere on the side, maybe there. And now let's go get this other wave function. So in this case, let's see, we go there, 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 there. Okay. Whoops. There we go. So let's paste it, and there we go. Okay. So it didn't end up where I wanted it to be, but it's okay. So now we wish to compare this expression with this one right there. But the problem is that one of them is in exponential form, the other one is in sinusoidal form, right? Sines and cosines. So we have to either go from the exponent form to sines, or from sines and cosines to the exponent form. It is, you can choose whatever, but it is easier to go from sines and cosines to exponents. So I would recommend that you do that. So doing that, let's see, we have that the patching wave function, this is, now we have a over square root of pi times minus z to the 1/4. And now instead of sine, right, we know that sine is e to the I times what is inside. So this is I 2/3 minus z to the 3/2. And then we have e to the I pi over 4 minus, and then we have e to the same thing, but with a minus sign. So minus e 2/3 minus z to the 3/2 e to the minus I pi over 4. And then we still have to divide all of this by 2i, which I will write down here. And then we have the cosine, which will be plus b divided by the square root of pi minus z to the 1/4. And then we get the cosine, which is e to the I, and now I'm lazy, so the same thing, times e to the I pi over 4, plus, that's the big difference, e to the minus, and the same thing, right? Times, of course, e to the minus I pi over 4. And all of this is divided by 2. Okay, so now we have written it in the way that we needed it, so we can get rid of this. So now let's compare it directly. So we wish to compare this expression underlined in green with this one. So let's begin comparing the positive exponents, right? Because positive has to be the same, negative have to be the same. They are linearly independent. So that's what we have to do. Now here we have this going with a positive. So we get 1 over h bar alpha inside of a square root times minus alpha x to the 1/4 times a. So I guess I can turn this 1 into an a. So a. And this has to be equal to, and now let's see, we have small a times e to the I pi over 4 divided by 2I square root of pi minus z, but we know that z is alpha x, so we can just rewrite it. And then we still have the b part because we have this other exponent here. So we get plus b divided by 2 square root of pi, and then we get another z, which is minus alpha x. So z is alpha x, but the minus sign was already there, 1 over 4. And then we have, just like this. So 1 over 4 and e to the I pi over 4. So here we can simplify things a little bit. We can factor out a lot of things. So first of all, we can actually, let me write it underneath because there's a few things we can cancel out. So this we can multiply by minus alpha x to the 1/4, and all of that cancels out. And then we can factor out a few things. So we have a, this is equal to, now let's multiply through by this and factor it out. So we get square root of h bar alpha divided by pi, right? So we factor out this pi and this pi. And then we have e to the I pi over 4, which we can also factor out. And we could also factor out this too if you want. I'm going to keep it inside, but you can factor it out if you wish. It will make no difference. A divided by 2I plus b divided by 2. Now, something we can do here, because I don't like to have an I in the denominator, so I will just multiply and divide by I, so I get minus a times I. Okay, just to make it a little bit cleaner, I like that notation more. So there we go, we now found an expression for big A in terms of small a and b. And we can actually, we know what a and b are, right? Because we found them, I think they're on the left side. We already found them in terms of d and c, so we can eventually plug them in. Now let's go for the next part. So we compared the positive exponents. Now let's compare the negative exponents. So basically everything that goes along this and this with everything that goes along, we need to go up. With everything that goes along this part basically. So this b and all of that. So let's maybe get rid of all of this right here. Actually, no, only this. Let's get rid of this so that we have some space. I'll move this to the side as well. So let's go to the side. Oh, did I lose it? Okay. All right, so I'll just put it to the side. And now we can go back to business. So from up here, we see that b divided by h bar alpha inside a square root times minus alpha x to the 1/4. This has to be equal to, we have minus a e to the minus I pi over 4 divided by 2I square root of pi minus z, which is minus alpha x to the 1/4. And then we have the term from the b part, so we get plus b divided, it did put it, okay. Divided by 2 square root of pi minus alpha x to the 1/4, and then e to the minus, which I will write here, e to the minus I pi over 4. And just like before, we can simplify a few things, so we can get rid of this part, we can multiply through, so we get b is equal to square root of h bar alpha divided by the square root of pi, and then we have e to the minus I pi over 4, and then we have factor of, we have minus a divided by 2i plus b divided by 2. And we can do the same thing as before, so multiply and divide by I, so that the I downstairs goes away. It gives us a minus sign, which cancels out this minus sign, so we get ai divided by 2. So there we go, this is b. So we have now found all 4 boundary conditions that the first section gave us, right? We went to x1, the first point of interest. We already found all information we could. I guess what we could still do is plug in our values for a and b. So let's do that. So plugging in, maybe I'll use yellow. So here for a, so a h bar alpha square root of pi, and then we have e to the I pi over 4. Now let's plug in a. So we have minus I over 2 times a, which as we can see right here is 2 times big D square root of pi, h bar alpha. Then we have plus b over 2, so we get c over 2 square root of pi over h bar alpha. Now multiplying through all of these square roots, they just cancel each other out. And this 2 cancels they cancel out. So we end up with this. So minus I times d, I'm just going to write it a little bit closer together, plus c over 2. So that is what we are left with for A. And doing the exact same thing for B, right? This part will cancel out when we plug this in. And then we have e to the minus I pi over 4. And then in this AI part, right, this cancels out. So the 2's cancel out again. So we get di plus c over 2. So the same thing, of course, but with a negative here. And there's also that other sign that is different. So there we go. We now found A and B in terms of D and C. However, let's go back to what we actually want to find. We want to find F over A. So we need to somehow relate A and F. So we need to do what we just did again. So the procedure will be basically the same, but of course now in the other region. So now we go to region number 2. So now we go here. So let's go grab our result, which is somewhere over here. Let's move it to the side. Oops, I meant move this. Move it to the side. And let's get to work doing the exact same thing. So in this case, we are no longer going to be using these 2 expressions, but rather these 2, because we are now in the other regions, right? This is the intermediate region. So now something that we will want to do is move the axis to x2. However, notice that although this expression does depend on x2, this expression doesn't. There is no x2 in this wave function. So if we move all of our expression to x2, we will have simplification here, but not here. This depends on x1. And having x1 is going to be really, really, really annoying. So if we don't do something about this, it's going to haunt us for the rest of this problem. So for that reason, let's take a moment and take a look at this wave function to see what we can do about it. So let's just write it as region 2. And here we have 1 over the square root of the momentum. We will not go into detail as to what it is just yet. C e to the 1 over h bar. And then we have this integral. However, what we would like there to be is we have to introduce x2 somehow and get rid of x1 somehow. So something we can do is change the limits of the integral. Now we're going to do this legally, right? And you're going to see exactly why it is that we have this freedom. So take a look at this. So the integral will now go from x1 to x2. Now let me go to the image to ensure that this makes sense. So let me show you what's going on. So the integral went from x1 all the way to x, and that integral is for the region in between. So it says we integrate from x1 up to some point x, right? And that is, of course, variable. It depends on what x is. If x is here or there, the value of the integral will change, okay? So what we will now do is we will say, all right, let's integrate all the way to x2. So that means that we integrate over the entirety of this barrier, right? And that means that this is no longer variable. It is now a constant. We may not know what the number is, but it is a constant. So let's write this. So let me take a look. This is px prime dx prime. But for this to be legal, we have to subtract 1 over h bar and now the difference. So integral from x to x2. Right? So let's go back to the drawing to explain this. So basically what I did is we used to integrate from x1 up to some x2. But now I said, all right, let's integrate, sorry, this is x2 is right there. Let's integrate onto this x. That's what we did before. Now I said, let's integrate to x2, but I subtract integral from x to x2, right? That's all I did. I said, all right, this region here is the same as all of the green one minus this red part. That's what I did. It's nothing illegal, I swear. Don't call the math police. Okay. Now let's go back. Now that that is hopefully clear. And, well, we just have to finish writing this. Px prime dx prime. And, well, for the d part here, it's the same thing. It's literally the same thing. So plus d e to the minus 1 over h bar, integral from x1 to x2 of the absolute value of the momentum. And then we have, okay, it is minus, but there's already a minus sign, so it is plus now, right? Because of this initial minus sign. So plus integral from x to x2. And then we have absolute value of the momentum dx prime, and then we have is that it? Okay, I think that's it, right? Yes. Okay, so there we go. Now what we want to do is we can get rid of this minus sign here and simply switch the limits of integration. So go from x2 to x instead of x to x2, and we simply minus, right? Because integral of something a to b is the same as minus the integral from b to a, right? So that's what we're doing here. And doing the exact same thing on the other side, we change the limits of integration from x2 all the way to x, but we have to put a minus sign in front. Okay. And now the next thing that we will do is we know that this part is a constant. Again, right, because we're integrating from x1 to x2, there is no variable x. And this integral right there, I hope might be familiar to you, because that integral is integrating over the entirety of our barrier, just like we did in our previous case, right? When we are dealing with the transmission coefficient over some square barrier, we integrated the momentum over the entirety of the barrier. So it is kind of similar thing. So we could call this exponent, let's call it e to the gamma, where of course gamma is 1 over h bar integral from x1 to x2 and all of this, blah, blah, blah. And the other one here, this will be dE to the minus gamma. So let's rewrite this thing here. This is CE to the gamma plus this thing. I'm just going to rewrite it so it's not that far away. So that is integral from x, what was it? Okay, I already forgot. I'm sorry. From x2, okay, so 1 over h. Okay, let's do it like this. So e to the gamma, e to the 1 over h, integral from x2 to x, and then the momentum. Okay. So that is absolute value of the momentum. And here we do the exact same thing. So this will be e to the minus gamma, and then e to the minus 1 over h. I think I forgot to write 1 over h here, but it's all right. So 1 over h, integral from x2 to x, and this is what we already know, so nothing new here. Okay, so this is what we have now. And finally, what we can do is call, all right, let's say c prime is c times e to the gamma, and d prime is d e to the minus gamma. And that way, we simplify things even further. And by doing all of this, you may notice that there is no longer an x1 here. There is no x1. Right? We only have x2. So finally, we now shift the axis, right? So now we shift axis, and the x2 goes to 0, right? We put our axis at x2 so that x2 is now 0. Okay. So there we go. We had to do all of this in preparation before we could even begin working with our problem. Now we do exactly the same as before. Okay, so this was a difference, the difference, but of course now we are in a downward sloping potential. That is super important. So let me just look at it again. Before we were in an upward sloping, now it is a downward sloping, and that will be different in some places. Okay, so what is different? Well, let's begin by, because we want to plug everything into our WKB expression. So we need to find the momentum, right? And it is square root of 2m. And now be very careful, because what we have now is e minus, okay, let me remind you. So our potential linearized is e, and now we have plus v prime 0 x, but this thing here is negative. So this is less than 0, right? So be very careful. So we get e minus v prime of 0x. Now, keep in mind, which region are we talking about when we are discussing purely the momentum? Well, only the momentum, right? Without the absolute value, it appears when x is greater than 0, right? So when we are dealing with positive values of x. It's always good to keep that in mind, and you'll see why. So here the e's cancel out, we get square root of 2m, and then minus v prime of 0. But v prime is already negative. So minus v prime of 0 will give us the absolute value of v prime of 0, right? Which is always positive. And then we have x. Okay, and why is that? Just as a quick reminder, so if you have the absolute value of some number a, this is a if a is positive, and this is minus a if a is negative, right? And in this case, what we had was precisely this, right? That's why we can write it like that. Okay, just a quick reminder in case there's any confusion about that. Okay, now we do the same trick as before. We multiply and divide by h bar squared so that we can rewrite this as alpha, right? Because this is alpha cubed, and then we have x. And h bar, of course, h bar squared, which we can take out. So we get h bar, and then we have alpha to the 3/2 and x to the 1/2. So this is the momentum. And to notice, of course, that the momentum is real because x is positive. That's why we always have to keep in mind. Sometimes you can realize that you used the wrong expression if you see that your momentum comes out to be complex. Okay, now the absolute value of the momentum. What's going to happen here? Well, the momentum is this expression, but the absolute value comes in the region where x is negative. So what we need to do is add a minus sign. So h bar alpha to the 3/2, and then we have, instead of just x, minus x to the 1/2. Why is this relevant? Because this occurs when x is negative. So in that region, we get, I don't know, x is -5, but we already have a minus outside, so they cancel out, and our momentum is real, which is of course what we need. Okay, now we need to integrate these two, but as you can see, they are exactly the same thing as before. So the integrals will come out to be the same. So integral of the momentum, let's just think back to our limits of integration. So what are the limits of integration? In this case, it's from, it's here. So it's from 0 to x. So this integral goes from 0 to x. So that means that when we integrate this thing, we get h bar, we get this 2/3 h bar alpha minus alpha x to the 3/2. And when we integrate just the momentum, the limits are from x2, which now is 0, to x. So in that case, so from 0 to x, and momentum of x here. And this will give us 2/3 h bar alpha x to the 3/2, right? This is the same as before. Okay. So now we have everything that we need. So let's actually write down our wave function. So let's go for it. Now, the first part of the wave function we have already figured out. It's this part right there, which is not quite showing. There we go. So that is, let's see, w, let's write psi wkb of x. This is, so there's going to be two parts to it. First, we have 1 over the square root of the absolute value of the momentum, which is this right there. So we get 1 over the square root of h bar. And now this will be, as before, 3/4. So we'll put alpha in here. And the other alpha we will put alongside with the minus x. So we get minus alpha x to the 1/4. Again, this is just preference. You don't have to group it like this. You will get to the same result. Then we have c prime e to the 1 over h bar times this in the integral with the absolute value. So this one right there. So we get 2/3, the h bar cancels out, minus alpha x to the 3/2. Then we get plus d prime e to the minus this same thing. So 2/3 minus alpha x to the 3/2. Okay, and now we have to go for the other one, which is 1 over the square root of the momentum. So here we get h bar alpha and positive alpha x to the 1/4. And then we have f times e to the I integral of the momentum, which is 2/3. The h bar cancel out, right? So that's why I didn't write it down. And finally, alpha x to the 3/2. And there we go. So this is the WKB wave function. All that we need are the patching wave functions. However, here is where you have to be very, 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 very careful. Okay, so if you did my other problem where we found the connection formulas for the downward sloping potential, you may already know this. But if not, you have to be very wary, because these functions are for z smaller than 0, z greater than 0. And in the previous case, z and x were both positive and both negative at the same time. But this time, because we are in a downward sloping case, as I wrote down here, I don't think you can see it, I'll rewrite it. So z is minus alpha x. So this time, when z is positive, x is negative. When x is positive, z is negative. Okay, so be very, 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 very careful. So, for example, if we want to take this z greater than 0, so what we need is we want the patching wave function to turn into the WKB wave function. So we need to compare this part, this right there. We want to compare it with the corresponding part where x is smaller than 0, which is this. So this is x smaller than 0, x greater than 0. So these are the ones that we have to compare. Honestly, as a quick tip, if you have to compare something that has an exponential without an I and something that has an exponential with an I, you did it wrong, okay? So, for example, if we have to compare e to the minus 2/3 z to the 3/2 with something that is e to the I, you did something wrong. You cannot compare those directly. Okay, so let's copy this quickly take it to the side, and the procedure is going to be the same as what we had before. Okay, I think I need to move here. There we go. So this is for z positive, which means x negative. So we have to compare this with this part right there. So let's begin with the positive exponent. So this part with this part. So what we get is that c prime divided by h bar alpha in a side square root minus alpha x to the 1/4. This is equal to, and now we go here. So there we get, and by the way, just keep in mind that z is minus alpha x, right? So that's why, don't get scared that there's a minus sign here and not down there. Okay, and then we have b over the square root of pi and z, which is minus alpha x to the 1/4. So from there, let's see, we can find that b is c prime times the square root of pi. So of pi divided by h bar alpha. Yes, there we go. This is result number 1. Now let's compare the other exponents, the negative exponent. So by doing that, let's see, we have up there d prime. So we get d prime divided by h bar alpha inside a square root minus alpha x to the 1/4. And this has to be equal to a divided by 2 square root of pi z, which is minus alpha x to the 1/4. And all of this gives us that a is equal to d prime square root of pi divided by h bar alpha, and we have to multiply by 2. So there we go. These are our first two results. So let's move them to the side, and we will repeat the procedure with the other region. So this is for the region x smaller than 0, which means z greater than 0. So now let's get rid of this. We already used it. Thank you very much. And now let's go get our other wave function. So the other wave function is this one. However, it is written in terms of sines and cosines. So we need to turn it into a complex exponentials. However, we already did this. I hope I didn't delete it because I don't want to do it again. Let's see. I did not delete it. It is this thing right here. Okay, great. So let me just select it so I can move it. And that way we don't have to write it again, which is very nice. So copy, and now let's go back all the way. I'm lost here. Okay, so there we go. Okay, it's a little bit off to the side, actually more than a little bit. All right, so let's move it. Damn it. There we go. Okay, so now let's begin comparing. So we want to compare the exponents. So notice that there is no negative exponent here. So we need 0, right, from here. So this is plus 0 e to the minus I, etc. So 0 has to be equal to everything that has a negative I here. So minus a e to the minus I pi over 4 divided by 2i square root of pi minus z, which, well, I guess it doesn't matter if we write it as minus alpha x. And then we just add the other negative term, which gives us b e to the minus I pi over 4 divided by 2 square root of pi and times this z. Now, of course, alpha times x, this is not going to be 0 here. We don't have to worry about it. So we can simply multiply by this and we get rid of it. We can multiply by 2. We can multiply by the square root of pi. So, and we can multiply by e to the minus I pi over 4. So this cancels out as well. So all that we are left with is going to be, let's see. So 0 is equal to minus a divided by I plus b. But we can write this as a times I. So there we go. So this is our first condition, that AI plus B has to be equal to 0. So once again, let's just take this, move it to the side, and keep it there for later. So we put this over there. And now we get rid of this expression, and we now go for the other one. So now we go for the positive exponents. So the positive exponent in our WKB function is f divided by square root of h bar alpha times alpha x to the 1/4. And this has to be equal to a divided by 2I square root of pi. And here we have minus z, but z is minus alpha x, so we end up with alpha x to the 1/4. And then we have e to the I pi over 4. And what else? Then we have plus b divided by 2 square root of pi, again, alpha x to the 1/4, e to the I pi over 4. Okay, now let's write down f. So f, let's see, we can simplify by getting rid of this, and we can factor out a few things. So f will be the square root of h bar alpha divided by pi, and then we have e to the I pi over 4. And all of this, let's see, we already used this, and this. And then we have a divided by 2i, so minus ai divided by 2 plus b, right? I simply rewrote this I in the numerator, as we have done many times already. And there we go. So let's now put it with the rest of our newly found expressions. And now we can combine some of these. So let's go here. So there's a few things to note. Now, of course, AI plus B, we can find from here, for example, that B is equal to minus AI, and by the same logic, then AI, or rather A, this is going to be equal to, let's see, we get minus B, and in order for us to get rid of the I, we can divide by it, and we get B divided by I, which is BI and times minus. Okay, there we go. So we can find B in terms of A or A in terms of B. It is the same thing, basically. And why is this relevant? Because now we can find, we can use it in here in the expression for F. And now let's take a look at what happens here. So from here, we get that F is h bar alpha divided by pi. Well, this hasn't changed. And now here, we can write this in terms of whatever we want. So we can write it in terms of, I don't know, let's get rid of minus ai. So we write this as b over 2 divided by, oh, I missed a b over 2 here, by the way. I'm sorry about that. So plus, this is another b over 2. So we end up with simply b. So just b. ei pi over 4 times b. I guess I should stick to the same color. And now doing the same thing, but getting rid of b instead of getting rid of a, we get f is equal to the same thing, h bar alpha over pi e to the I pi over 4. And then we write minus ai over 2 minus ai over 2. So basically, just minus ai. There we go. So now we found f in terms of b and a. So now we can turn it around. We can find a and b in terms of f. And why is that important? Because then we can go to these equations which have c prime, but c prime is basically c, right? Because it's c times e to the, I don't know if it was gamma or minus gamma. And then we relate f and c. And if we relate f and c, we can then go back to the equation that we had at the beginning that relate a and c and a and d. So we can then relate a and f, which give us the transmission coefficient. So that is the plan. So we have already done the hard part. Now we simply have to solve here. So now let's go and find b. So b is going to be the square root of pi divided by h bar alpha times e to the minus I pi over 4 times f. And then from here we see that a is going to be, let's see, square root of pi over h bar alpha e to the minus I pi over 4, and we need to multiply by I, so we get rid of that minus sign. So this is positive, so we get I times f. Okay, now we want to plug this into our expressions for b and c. So maybe let's take these expressions and bring them a little bit closer so that we can actually use them. Okay. Now let's plug them in. So from this one, for example, we see that square root of pi over h bar alpha e to the minus I pi over 4f, right? This is that, is equal to c prime times the square root of pi over h bar alpha. So these square roots cancel out. And we get that c prime is this. But c prime, well, what was c prime? And I'm genuinely asking, I don't recall. C prime is c e to the gamma. Okay, so c prime is, so this is c e to the gamma. So that means that c is equal to f times e to the minus I pi over 4 e to the minus gamma. And now we related c and f. Now, let's do the same thing, but for d. So we need this thing right there. So a is this, and it's also this, so let's set them to be the same. Now, of course, this and this will cancel out, the square roots, so no need to write them down. So we get that 2d prime, this is equal to e to the minus I pi over 4 times if, and this, of course, since d prime is d times e to the minus gamma, we get that this is 2d e to the minus gamma. So from here we find that d is e to the minus I pi, okay, that doesn't look good, pi over 4 e to the gamma if divided by 2. So now we found c and d in terms of f. So finally, our last step to find the transmission coefficient is going to be to take these expressions and plug them into the ones that we found quite a while ago. So let me just quickly move back and see where they are. So I think it's right here. There we go. So here we have an expression for a and b in terms of d and c. Now we're not interested in relating b and f. If we wanted some sort of reflection coefficient, we could go for it, but that is not the case. So let's plug them into a. So both of them go in there. So a is equal to e to the I pi over 4. And now plugging in d, we get, well, the i's will cancel out, so the minus sign cancels out as well. We get another minus sign, we get a minus minus, so they cancel out, and we get e to the minus I pi over 4 e to the gamma times f divided by 2. And then when we plug in c, we get, let's see, f e to the minus I pi over 4 e to the minus gamma divided by 2. So these exponents will cancel out, and then we can factor out f over 2, and we get e to the gamma plus e to the minus gamma. Now from this, we can see that f divided by a, which is what we have been looking for this entire time, is simply 2 divided by e to the gamma plus e to the minus gamma. Okay, that doesn't look good. I'm going to write it like this. Plus e to the minus gamma, right? Because we multiply by 2, we divide by this, yes. And now squaring this and getting the absolute value, we get, so this thing squared, we get 4 divided by e to the gamma plus e to the minus gamma squared. However, this doesn't really tell us too much, so let's manipulate this algebraically so that we can find something that is a bit more helpful. So let's multiply and divide by e to the minus 2 gamma, e to the minus 2 gamma. And when we do that, we get 4 times e to the minus 2 gamma. And in here, we can put this inside, right? E to the minus 2 gamma is e to the minus gamma squared. So we multiply all of this by e to the minus gamma. So this part, it will cancel out and we get 1. And then we have plus e to the minus 2 gamma. And then we have this thing squared. Now, let me maybe get rid of this because it doesn't look very good there. Okay, so what is this expression? Now, this is precisely what we defined as our transmission coefficient. But notice that the WKB approximation is valid in the regime where gamma is very large, which means that e minus 2 gamma is very small. So that means that the denominator is basically 1, right? Because this thing is very, very, very small. So the transmission coefficient is approximately 4 times e to the minus 2 gamma, which means, right, that we basically recover that the transmission coefficient goes as e to the minus 2 gamma, minus 2 gamma, which is what we have found in previous videos for other cases, but it's good to know that it's still valid even in this case. So basically, what this means is that if you have this situation, all you need to do is calculate gamma, which is the integral from x1 to x2 of our momentum, and you can just plug it in there, and you don't even need to solve the Schrödinger equation, right? We only have to solve it for this particular case. Once we are basically to prove this formula. Now that we have the formula, any sort of problem that has this kind of potential, you just use this result and you're done. So there we go. I hope that this video was useful to you. If it was, please consider leaving a like on the video, commenting and subscribing, and maybe checking out my Patreon link in the description. I'll see you in the next video. Thank you very much for watching.